Transportation seminar. My name is Miguel Figliosi from Civil Engineering. With my colleague Jenny Liu from Urban Planning, we're organizing the seminar. And today we have the first of the students presenting research related to TRB presentations and papers. So the first topic is going to be Huajie. Sorry, I cannot pronounce very well Chinese names. Talking about multimodal travel demand modules, and then the presentation is going to be around 20 minutes. We'll have 5 minutes for questions, and then in the second part, we're going to have Alvaro talking about bicycle and pedestrian crashes in the state roads, the severity. So again, 20 minutes and 5 minutes questions. So that's how we are going to organize it. So again, if you are taking the seminar for credit, please sign up. Now, it's all yours. So,
I just keep this.
Should you keep the microphone? The mic?
Oh.
Clip it in there.
Oh, thanks. Hi, hello everyone, and thanks for coming to. Oh, where is my notes? Oh.
I don't have your notes.
Oh.
Go ahead.
Okay. Before the presentation, let me introduce the co-authors. This research is a section of the research project supported by MITIGATION and ODOT. And Li Mingwan is the principal investigator of this project. And Brian Gregor works for Oregon State Analytics Company. And Tara and Tony are from Oregon Department of Transportation. And this research will develop a multi-modal travel demand module for the regional strategic planning model. And the regional strategic planning model is a performance-based tool for metropolitan government. Specifically, this model simulates a combination of different transportation and land use policies. And based on these simulations, the governments to select the optimal transportation policy and land use policy. So the regional strategic planning model needed to consider the potential almost all factors that might affect transportation and the land use system. So it integrates the factor into different modules. The multi-modal travel demand module is an important module. The purpose of this module is to estimate the travel demand by driving, transit, biking, and walking. And our research, this presentation will focus on the model for estimated travel demand for the driving. And first, let's take an overview. Take an overview of the regional strategic planning model. And the regional strategic planning model is a performance-based planning tool. It is first developed by the Oregon Department of Transportation. Originally, this tool is developed for assessing the greenhouse gas emission, and called the green step. And later, the Oregon Department of Transportation wanted to take more measures, such as household costs, health, and other measurements into consideration. So the green step is rebranded as the regional strategic planning model. And later, because the RSPM, the success of RSPM in Oregon, and later the RSPM is adapted nationally as the rapid policy assessment tool and the energy and emissions reduction policy analysis tools. This family of tools, they assess the different combinations of transportation and land use policies, and to evaluate how the transportation investment policies and land use plans will affect the transportation investment budget, and how they will affect travel behavior and thus influence desired community development goals. And currently, the Federal Highway Administration wants to merge this family of tools into the open source common framework called Vision for. This framework will facilitate the development of these tools, and the tools of this framework will share a common data store. So, and essentially, the SPM is an integrated land use and transportation model. It balances the speed and the interactivity of simple model and the flexibility and the research realism of the micro simulation. This flow chart shows the steps of the ISPM, and there are totally 16 sequential steps, and these 16 steps are grouped 4 sections. First is to define households, and second is estimate the VMT and characterize the vehicles, and balance the VMT and the travel costs. This research will focus on the 5th step. This step calculates the household daily VMT. And currently there are 2 definitions for this step. First one is it synthesizes annual daily VMT. This is because when the model is developed, it uses the 2001 National Household Travel Survey. And in this data set, there's no incomplete information about the daily VMT. So it synthesizes the daily VMT instead of directly a model of the daily VMT. And the second one is current calculation only include a limited set of built environment variables. So our motivation of this research is solve this deficiency. And the first motivation is we want to capture the connection between built environment and the travel for rapid policy evaluation. And we will use recent NHT as data, and it is 2009 National Household Travel Survey. And we also will add built environment variables from smart location data. The second motivation is to develop a module for Vision 4. And in the whole process from data processing to the final model estimation and the report and the document compiling, we all integrated in the statistical language R and as a self-contained package in the Vision 4. So the module in the Vision 4 can work interactively with other modules. And the third motivation, we want to follow the best practice for model development recommended in the literature. In our research, we not only does variable selection, we also conduct model selection. So to fulfill these motivations, we create a unique data set. This unique data set is created through combine several nationwide data sets. The first one is 2009 National Household Travel Survey. This survey collected trips taken by all members of the surveyed household on travel day, as well as social demographic characteristics. The smart location data set is a nationwide built environment data set. The built environment variables are integrated into 4 categories: density, diversity, design and destination and distance to transit, such as population, household density, land use diversity, neighborhood design, and distance to transit service, and so on. Through the smart location data set provide some built environment variables, but all these variables are at the track level. So we also want to add some urbanized level built environment variables. So we use we collect transportation supply data from national transit data set and urban mobility reports. So because transit service is not available for the urbanized area, so the data set is divided into two segments. One is the UCA segment, and another one is the non-UCA segment. And we will estimate separate model for two segments. And this is this descriptive statistics of the our data set. And the annual average daily VMT is our dependent variable, and the independent variable includes the household and socio-economic characteristics, built environment, and transportation supply. For the annual average daily VMT model, the household annual average daily VMT is regressed on household characteristics, built environment, and the transportation supply. For this model, we choose four model structure, and this four model structure is common in the literature. The two-step model and the hurdle model are special model for dealing with the independent variable with lots of safe values. Because we use survey data, so if the household do not drive on the survey day, the household daily VMT is 0. So this plot shows the distribution of the annual average daily VMT. And you can see there is a lot of 0 values. And the power transformed linear regression model is because this distribution is not normal. We want to make the dependent variable has a normal distribution. After the power transformation, the distribution of the annual daily VMT looks like it's close to the normal distribution. This plot shows the distribution of annual daily VMT after the power transformation. The first one is the semi-log regression model just take a log of the daily VMT. Semi-log means it only logs the dependent variable, but it does not take a log of the independent variables. This is our model. In the modeling process, we conduct variable selection and model selection. For the variable selection, we based on behavior validity and model goodness of fit and statistical significance. The behavior validity requires the variable selection is consistent with the theoretical and empirical research. In the variable selection, we control for household social demographic variables before adding built environment variables and transportation supply variables. Because in each category, 5D category of the 5D variable, and the built environment variable have high correlation. So we choose at least one variable from each category of built environment variable that has the best improvement for the goodness of the model fit. And so model selection, we use K-folder cost validation. And so K-folder cost validation is an efficient approach for cost validation. And simply speaking, is this approach randomly select a portion of the data for model validation, and the rest of the data is used for model estimation. And for model selection, we choose the model structure with the best accuracy performance. And here is this table shows the average K-folder cost validation for the model structures. You can see we estimate the 4 structure for both UCA and the non-UCA segment. And you can see this table shows the 2-step model, and the power transformed linear regression model has the best accuracy performance. The root mean squared error is lowest. And we finally choose power transformed linear regression model for both UCA and non-UCA segment, because this model is easy to use and the computation performance is good. So 2-step model takes a long time to calculation, and the interpretation is not simple. And so this model this table shows the detail of the power transfer model. Here, it works on my laptop. Here, I want to show is you can see almost all household socioeconomic variables has affected sign, and we capture this variable is vehicle per driver in the household. We capture the non-linear effects of the vehicle per driver in household on the driving. Here we use a cubic spline approach, and for the built environmental variables, so here it's this here. So this D1B is the population density variable. It should be negative, but here it is positive, and there's land use diversity is D2A. Here it has a positive. This I think it is because we already added the check population density and the employment within the 5 miles buffer. And in addition to the built environmental variables themselves, we also conduct interaction tests. For this interaction test is transit revenue mile per capita in UCA with frequency of transit service at the local level. This means good access to transit in UCAs with extensive transit network will have extra effect on reducing driving VMT. And next, this plot shows I mentioned before the vehicle per driver is the relationship is non-linear. This plot shows the vehicle per driver, the relationship between vehicle per driver between the annual daily VMT. And the x-axis shows the percent change to the vehicle per driver, and the y-axis shows the average annual daily VMT. And when x is 0, this shows the current situation in the 2009 National Household Travel Survey. And zero means no change. So based on current vehicle per driver, the annual average daily VMT in UCA household is about 48, and the FCI is 100% decrease. This means there is no vehicle in the UCA area. So annual average daily VMT will drop to around 5. And the FCI is 1% increase for the vehicle per driver. The annual average daily VMT will increase to around 68. And the next 100 increase from 100 to 200. The increase in the annual average daily VMT is less than the first 100% increase. So this captures a non-linear relationship between the vehicle per driver and the annual daily VMT. And the non-UCA segment have a high elasticity than the UCA model. So we get some conclusion for this research. First is the power transformer model is chosen among a handful of model structure options for its simplicity and prediction power. And this annual average daily VMT model presents in this paper is the first model utilizing such a nationwide dataset with high resolution built environment variables while controlling for household social demographic characteristics. And also, this presentation only covers the annual daily VMT model for driving. Other model for transit, walking, and biking is also included in the multi-modal traffic demand module. And the implementation of the multi-modal traffic demand module as an open source R package follows the best practice outlined in the Vision for Development Guide and went through a contribution review. And in our research, we have quite a large sample size. The 2009 National Household Travel Survey have 150,000 observations. And there are more than 19 variables in the building environment, building smart location data set. So model selection techniques such as stepwise and Bayesian averaging techniques are only helpful only to an extent. So we think machine learning techniques may be a direction we will explore in the future for the variable selection. And so this project is supported by MITIGATION and ODOT. Thanks.
Can you help me with this, please? I'm trying to move this file. Hello everybody, my name is Alvaro Caviedes. Today I'm going to be talking about crash severity and vulnerable users as pedestrians and bicyclists. This was my topic of my thesis in my master in civil engineering as well. So I'm going to start talking about why is this topic important in the context of states, like what we did in the problem statement, what was our research, then the data and methods we used, the results we got, and the recommendations we have. So the state of Oregon is expecting a population growth of 30% by 2040. This means we are going to have more pedestrians and bicyclists on the road. States and cities like Portland have to prepare for this with infrastructure, and with infrastructure I mean good infrastructure. Additionally, the state of Oregon, they have implemented the Oregon Transportation Safety Action Plan, where they basically have the Vision Zero statement, where they want to decrease the fatalities for vulnerable users for zero. And this is like a big thing. The problem is that for urban areas, there is a lot of research, so they can get good feedback on what to do. But for rural and suburban areas, there is not too many information. So this is the focus of this research. We also looked into the lead review, and we found that most of the research in terms of severity is focused on the driver's perspective. So there are a lot of things that can improve their safety, but what about pedestrians and bicyclists? And also, the few studies that have like a static crash severity for pedestrians and bicyclists only focus on crash frequency. So crash frequency means like how many crashes are happening in any type of road, while crash severity means what kind of facilities increase the likelihood of a fatal crash when it happens. We also found that in the lead review, in the background, we found that studies have found that urban environments like land use can be useful to predict a crash frequency. So like in areas like urban areas where there are like a lot of pedestrians or bicyclists in the streets, there are going to be more crashes. But this is cannot be applied to crash severity, because there can be a case where there are no cars, there are no pedestrians at all, like at least one pedestrian in this rural area, but cars are going very fast here. So it's going to be, if a crash happens, it's going to result in a fatal one. Other studies have also found that risk factors can be grouped in these categories. So the location of the crash, environmental conditions such as weather, the crash characteristics such as if a passenger car was involved in the crash or a bus was involved, the road characteristics, so like if it was in a local street or if it was in an arterial, demographics such as gender and age, and traffic characteristics such as volume of the road. So like based on this, basically lead review and like background we did in the state of Oregon and the lead review, we proposed this problem statement. So what we did was exploring the risk factors of crash severity for pedestrians and bicyclists in the Oregon highway network system. In other words, we want to find which are the risk factors that increase fatal crashes if one crash happens for bicyclists and pedestrians. We have used the Oregon State crash database from 2007 to 2014. So basically, when a crash happens, like people have to, or the police, or in Oregon, like people can fill out this like big questionnaire where they give like very detailed information of the crash. The problem nowadays, there are like a lot of problems, I'm going to mention a few, is that this crash database only includes crashes that include a car. So if a crash was involved a bicyclist and a pedestrian, it's not going to be in this database, which is like, it's very sad too, because if it was severe or fatal, like as researchers, we cannot find out what was the main cause. Other problems is that if a crash happened and result in property damage under $1,500, it's not going to be reported either. So if a crash got involved in a crash with a bicyclist and the bicyclist was using like a cheap bicycle, it's not going to be reported here either. And yeah, those are the main problems. Also, we found that when we were like playing with the database, we found that when a pedestrian is involved in a crash, it's not going to be like a minor crash in most of the cases. It's going to be very like severe or fatal. So there is kind of like a bias in the database while like doing our research. We also use the ODOT TransGIS database. This is the Department of Transportation spatial database, where they have like the network of the highways in the state, and also they have information about the volume and like road characteristics. And we also use this spatial database called Neighborhood Concept, developed by Currans et al. It's basically a spatial database where it tells you what different land uses are in Oregon. So if this area is like rural or suburban or like it's urban, and that can be useful for this research to see where the crash was located. So the way the crash database code the severity of a crash is like with this scale called CAPCO, where K means kill and it goes down to O, where it's only property damage. Again, with this I only mean crashes that were above $1,500, but were not severe. So based on this, we like predicted our models and found what were the main risk factors. In terms of the database, we found that for pedestrians, there are around 6,000 crashes. Around 30% of them occurred at highways. And for bicyclists, there were around 7,000 crashes, and 20% occur in state highways. We also found that most of those crashes occur at intersections as opposed to segments of the road. So now in terms of the descriptive analysis, I'm going to talk about like different characteristics of the road to see how the crashes look like in the state of Oregon. So first of all, in terms of location, we found that, so I'm going to only show crashes that were fatal or almost fatal. So most of the fatal or almost fatal crashes for pedestrians and bicyclists occur at segments of the road. In terms of land use, we can see that there's like an almost similar pattern for almost fatal crashes, but in terms of fatal crashes at suburban and rural areas, we are seeing more. So what this tells us is that in these areas, it's likely that drivers are going faster than in urban areas, and there is also less traffic management like devices, so there is not any restriction for how fast a driver can go. In terms of environmental conditions, we found that when it's dark and there are no like street lighting, there are more fatal and severe crashes as when it's like in daylight. And in terms of weather, we found that it's kind of like the same, but we found that when there's bad conditions, there are more almost fatal crashes. But it's interesting that the difference is not too much, so we can kind of hypothesize that in bad conditions, drivers are more careful when they are driving. So like basically they're more like aware of bicyclists and pedestrians. In terms of crash characteristics, as like we can like predict, when the driver is intoxicated with alcohol, like the crashes tend to be fatal or almost fatal. In terms of user location, we found that for pedestrians, when they were like crossing in like crosswalk or mid-block, it was better than when they were crossing like in the middle of the roadway. And for bicyclists, it was the same. When they were in the roadway, it was very bad for them in terms of fatal crashes. When they were in the bike lane, there were no fatal observations. In terms of, again, crash characteristics, vehicle type, if a crash happened with a heavy vehicle involved, it tended to be fatal and almost fatal. And if the vehicle was like moving straight rather than turning, it was also fatal. So this also is related to speed again. So when a car is driving, it's turning, it tends to decrease the speed. So we can see that it may be more frequent that a crash is going to happen at an intersection, but it's going to be less severe. In terms of traffic conditions, so for this we use this definition called AADT, is annual average daily traffic. That is like kind of tell us how used is a highway. So we found like only using AADT for trucks, like as AADT increases only for trucks, like fatality also increases, and this is true for pedestrians and bicyclists. And finally, for road characteristics, we can like see like in terms of posted speed limit, this trend that as like speed limit increases, like crashes tend to be like fatal and almost fatal. And then road surface, we found something similar than weather. That in dry and wet conditions are almost similar, and it's likely because drivers are more cautious. So we also did another analysis for the descriptive part, just kind of to see the crash frequency in terms of something we call risk factor. So we wanted to see which characteristics of the roads produce more crashes by controlling for exposure. So exposure is this concept that can tell you how much a road is used. So there's good data for cars, like in the databases, but there is like a lack of data for pedestrians and bicyclists. So you have to kind of use like these definitions like you make up trying to like control for this. So what we did was just creating risk factors in terms of the percentage of crashes in like any type of road. In this example, 1-lane road, and divided that or controlling that by the exposure that we control by VMT, that is vehicle miles traveled in that roadway. So we did that for number of lanes, road width, and road classification. And in general, we find that all of these things, we can relate it to higher speeds. So as the number of lanes, road width, and road classification like increases, the speed is going to increase, and as well like the number of crashes, the risk factor. So we can see from 1 to 4, crashes increase, risk increases, from 10 to 40 in terms of width increases, and from a local street to an arterial street, risk factor also increases. We see in like this like decreasing like lanes with in roads with 3 lanes, or like roads with 30 feet, 40 feet, and it is because there are not too many observations of crashes in those roads, and also because 3-lane roads basically is a road with 2 lanes and a middle lane, which is like if a pedestrian is crossing and it's in the middle lane, it's going to be kind of safer than being like next to the cars in a fast lane. So now I'm going to talk about the results. For the methodology, we use this statistical tool called ordinal logistic regression. Like it basically tells you how much likely, if a crash happened, how much likely is going to be fatal or almost kill, as opposed to being a minor crash. We like, based on that model, we like created different individual models to assess every variable at a time to see what was the direction of the relationship. Then we use pool model that was just putting all the variables at the same time to see like if they interact or not and how the relationship changes. And then we conducted a sensitivity analysis that is helpful to like see which are the main risk factors after you make your model. So I'm just going to talk about the pool models. So we control for socio-demographic variables, crash characteristics, road characteristics, and traffic conditions. So for the pedestrians, we found that if a crash happened, these risk factors will increase the likelihood of a fatal crash. So if a crash happened with an older use involved, if the driver was intoxicated, if there was a bus or truck involved, if the crash was occurring in a segment of the road as opposed to the intersection, if the pedestrian was in the roadway as opposed to crossing in the crosswalk, if the car was going straight rather than turning, if the posted speed limit was over 50 miles per hour, arterial, if it was dark and no street lighting conditions, and if the ADT for trucks were higher than 700, all of these will like predict a higher likelihood of a fatal crash. In terms of bicyclist crashes, we only found like 3 significant variables. So crash location, movement of the car, and also ADT for all the cars. And this is an interesting relationship because we found that when there are a lot of cars using the roadway, the likelihood of a fatal crash is going to decrease. And it's because when there are more cars, they are going to go slower. So more crashes are going to happen, but there's going to be less fatal crashes and almost fatal crashes. In our single model, we also found other characteristics significant that were not here, such as land use. So we found that in suburban and rural areas, there are more fatal crashes than in urban areas. But this variable can kind of like predict other like high, like posted speed limit or number of lanes or stuff like that. So that is why it's not in the model. Also time of the day. So off peak hour, we found that there are more severe crashes, like the time of the night, rather than peak hour where like there's a lot of congestion. We also developed a model just using road and traffic characteristics because by using that, we can kind of tell, like these are the things that you can really change in your infrastructure to like save more lives. And we found that for pedestrians, so this is everything that is higher than 1, it means that it increases fatal crashes, and lower than 1, it decreases fatal crashes. So for pedestrians, we found that again, like no street lighting, arterial, high speed limit, segment of the road, and like ADT, all of those increase likelihood of fatal crashes. And for bicyclists, we only found that location, segment of the road, and ADT, when it's high, like it decreases the likelihood of fatal crash for the same reason as I said before. Now we conducted the sensitivity analysis to see, so from the variables I found before, which are the main ones, like the most important ones. So to do this, we use the model. So in our model, we are predicting the probability that a crash is going to be fatal in terms of these things. So we have a baseline scenario where we predict the probability of a crash severity, where all the things that can happen are like, okay, not the worst thing. So a crash happened where it was daylight, it was in a local street, cars were going very slow, like the pedestrian was crossing in a crosswalk, and like the ADT for trucks was very low. So in that scenario, that is like the safe scenario, the probability of a fatal or almost fatal crash is 7%, which is fine. And then after that, we compare that scenario like with like a bad scenario. So in this case, in this example, I compared where like a safe scenario, but I changed the light conditions. Now in the crash happening in dark conditions. So in this scenario, now the probability of a fatal or almost fatal crash is 16%. It means there is like an increase of 8% with the baseline scenario. So we did this with all the variables we found in the model, and we found that dark and no street lighting, arterials and location segment of the road were the highest, were the worst risk predictors for a fatal crash. We also calculated the worst case scenario, that it was like the opposite of the safest scenario. So if you're like in the dark, in an arterial street, if there are a lot of trucks and cars are going very fast, like the likelihood of a fatal crash is going to be 60%. We did the same for bicyclist crashes. In this case, there were only 2 significant variables, and we found that segment was like 80% in terms of the baseline, which is like significant. So in terms of conclusions, like the main takeaways, just controlling for all the variables, we have found like age is very important. Like if a crash happened like in an older, like a senior person is involved, it's very likely it's going to be like fatal or almost fatal. Of course, like if like alcohol intoxication, if somebody's drunk, cannot control the car, it's going to result also in a fatal crash. Vehicle size, vehicle movement as well. And in terms of only road and traffic characteristics, we found that like the main thing is that everything that is kind of related with higher speed limits, it will end up bad for the pedestrians, for the bicyclists. So like posted speed limit, road classification, location of the user, all of are kind of like related to higher speed limits. We also found like light conditions, road surface, and land use, which is also related to the characteristics of the roads, are related to more fatal crashes. So what can we do with this information? So like one thing is educational campaigns. Our data doesn't like show this, but we kind of like suggest to do this in suburban and rural areas, kind of educate like drivers of big cars to like be careful of pedestrians and bicyclists, because normally bicyclists are in the blind spot of a driver of a very big vehicle. The same with training courses. More strict enforcement in terms of like people who are like not complying with the posted speed limit or with like alcohol intoxication laws, and also protection of vulnerable users. So all our results are telling us that first, cars have to go slower in terms to reach that vision zero ODOT has. And second, we have to like provide segregated facilities for bicyclists and pedestrians, which is like the obvious thing. Conclusion, so in terms of limitations, so the limitations I mentioned you before about the reporting, and there is also one that is underreporting. So like just doing this research, like reading, we found that 30% of the crashes are not reported. Sometimes like you get into a crash and it's not fatal, you kind of negotiate with the driver and like you don't report anything. Or there is the other case of hit and run, like something bad happened but it's not reported. Speed, so in this database, because it was mainly focused on state highways, there is kind of like a bias in like the posted speed limits, because in state highways, they're like the posted speed limit is very high. In future research, we advocate to like study this same thing, but including bike facilities, to see if a segregated bike lane will decrease the likelihood of a fatal crash in terms compared to a bike lane that is just next to the road, just like a painted bike lane. And we also found that special pedestrian signals are not very well reported in this database. For example, flash beacons, we found that it was worse for pedestrians. And when we digged into the data, we found that this was not reporting very well. Like it was like the people were confusing a stop sign with a flash beacon. So it's very hard to study this. And with that, I close my presentation and I'm open to questions. Thank you.
So in your research, you found that the location of either the pedestrians or bicyclists being in a segment of the road was highly correlated to whether the accident would be fatal. Why, in your recommendations, didn't you gear your education campaign towards them, kind of focus instead of just on driver behavior, if people are crossing at non-designated crosswalks, if that's how they correlate in their death, why wouldn't we focus on educating them to not cross them unmarked crosswalks?
So that's a good question. So one of the big things about Vision Zero is not to blame kind of the user, and that also includes the driver, but blame the infrastructure. So like what they're trying to do is just not say like, even like with drunk drivers, they are not saying like, oh, like this is your fault, it's the fault, but it's like, what can we do in our infrastructure to like allow people to make mistakes? Because we are humans and we are going to make mistakes. So that's why mostly of all of these recommendations aim to infrastructure rather to like the user. Although yeah, like I focus a little bit on the driver too, which is unfair.
So how do you explain in the difference you saw, and this is only pertaining to bicycles, between the descriptive data you were able to extract and what the model was telling you?
So like the big challenge of the bicyclist data, it was that most of the crashes didn't happen in state highways. Like most of them happened in the like urban environments. But this was really focused on state highways. So that was like our main challenge at the beginning of like the whole project. Then in terms of the descriptive analysis, we saw that there were like differences in most of the variables, like intuitive, like higher speed means for like fatal crashes and etc. But when we started to control for other things, we kind of see that more things had like a higher weight than we thought. And this is related to the observations. Because there were not too many observations, we couldn't avoid that problem. In that same idea, for bicyclists, like if you're a bicyclist, you are not going to be in a state highway, like biking, So the people who were doing that were kind of like risk prone. So the data is also biased for high speed limits. So that's why we cannot see viability to like predict in the model what is a fatal or not fatal crash.
In some of the slides you mentioned versus
So we found that we explored the location of the crash. It was bike lane when the bicycle was in the crosswalk in the roadway. We found that the roadway was more prone to fatal crashes. But if you see the difference for almost fatal crashes, the viability was almost the same for all the bicyclists. And this is related to the same problem because there were not too many crashes in these facilities, and these facilities have kind of like the same conditions for like bike lanes. Like, and with that I mean like same posted speed limit, same number of lanes, road width. So you can see kind of that viability to tell what is really happening. And also crashes that happen in a bike lane were only 36. So that's like a very low number of observations to find something significant in the model.
I was just wondering if there's any information available on the databases that allow you to include variable things like how diluted lights are allocated in sectors that this would be considered.
Yeah, no, that would be great, but as how it is now, it's not The extent of like bicyclists in the database is just bike lane, where it was located. But it doesn't talk too much about the bicyclists in general. They talk a lot about the car, how is the car, like the Jeep, the model of the car, like how big it was. But for the bicycle, they don't have any information.
And actually,
yeah, exactly. And also, it also is related to the underreporting. So if a crash happens, like you can get into an agreement. If it's like a minor, you get into an agreement, so you don't have those observations to kind of like tell something about how to improve the infrastructure. Any other question?
Indication that Oregon's going to start taking those apps.
I do think, yeah, if you go to the Oregon Department of Transportation website, they have like very good strategies and plans that they are trying to aim for like this Oregon Transportation Safety Action Plan. And everything is towards that. Like now the problem is money. Thank you very much. Thank you.
You sign up. Sign up. Just make sure. Next week we're going to have more presentations from TRB. Again, 2 students, 1 from urban planning and 1 from engineering. So hope to see you this
For your presentation.
Yeah. Thanks for coming.
Oh, yeah. You said we're trying not to blame
The people.